This is a weekly summary of interesting news that is relevant for my distributed systems lecture at the Eastern University of Applied Sciences in Switzerland. My name is Thomas Boczek, and we will discuss today 4 topics. This blog post describes how a startup rebuilt the way its engineering team works. The reason AI coding agents like Claude Code and Codex changed the game so much that their old processes stopped working. Their new first rule is no coding before 10 a.m. Instead of jumping into code into the morning, engineers now spend the first hours in the day talking, aligning on objectives, and drafting prompts together. Only after that, they let AI agents do the actual coding. The core idea is an inversion of roles. Agents do the work. Engineers make sure agents can do the work well. And the team treats AI agents as the primary user of their systems. Code, naming conventions, and data structures are all designed for agents to read and understand, not humans. Code is no longer treated as a reusable library, but as a context that agents read and then regenerate. Data becomes the real interface between components, not function calls. And the team defines objectives and constraints first in one sentence. They do not specify how to build something, only what the outcome should be. They review output against objectives, not the code itself. If it works, they ship it. Each engineer uses their own ID and prompt style, but what is standardized are data patterns, objective specs, and component responsibilities. They also assume everything changes in 3 months, so they have to build modular and avoid lock-ins. Well, now for me, in January, I continued to work on my projects and wrote lots of working code. However, I did not write a single line myself. I was productive by supervising, correcting, and changing, but the actual code was written by AI. This is a complete workflow change, and this article reflects exactly that shift. This is also why I changed the group work in the challenge task to individual work. I believe that with generative AI, individual work is now feasible, and this gives you the opportunity to try this new way of working, if you have not done so yet. However, be skeptical. Can an agent reliably work overnight or on long tasks without going off track? Well, with my experience with the latest Opus 4.6, which I'm using, I made the experience that it can go into the wrong direction in the very first prompt, and I was hitting the stop button a lot. Also, this challenge task is a greenfield approach, which might be easier for AI assistants and may not work that in mature code bases. The next blog post is the following here. This post explores why compression is almost always worth doing in database systems and provides a mathematical framework for reasoning about the trade-offs. The core idea is that databases are bottlenecked on 3 resources: I/O bandwidth, CPU, and memory. Compression trades I/O for CPU. It costs CPU cycles to compress and decompress, but moves less data over the wire or from disk. The article defines a breakdown bandwidth formula. Compression is worth when the I/O time saved exceeds the CPU time spent compressing. Using compression level 4 on the sample set, here shows the break-even point is about 2.76 gigabits per second on a typical AWS instance with 1.25 gigabits per second network bandwidth. That compression level pays off. On a fast NVMe disk with tens of gigabits per second, a single transfer is so fast that the CPU overhead of compression would actually slow things down. However, the article argues that single transfer latency is the wrong way to think about data. Databases constantly read data and will saturate the I/O bandwidth before they saturate the CPU. And with 9.4 compression ratio, the logical bandwidth of 1.25 gigabits per second becomes over 11 gigabits per second. And the article then puts $1 on the value on this. On AWS, sustaining 1 gigabit per second on physical bandwidth costs about $9 per hour in transfer fees. With compression, that costs drops to $9 divided by the compression ratio plus a small CPU cost. And for the test data set, compression level 8 here, you see minimized the cost. The article also covers semantic encoding techniques like delta encoding, wrong length encoding, prefix encoding, and dictionary encoding. These are applied before entropy compressors. And in the scaling lecture, I mentioned optimized for bandwidth because bandwidth grows slower than CPU, so compress before sending. And now this article gives us numbers to back this up. In the next article, which is the following article here, this breaks down how Discord handles trillions of messages across its platform. The article covers both the architectural patterns and the specific optimizations Discord used to stay fast at scale. The Discord architecture is built on the actor model, which is a concurrency pattern. Instead of using shared memory and logs, each actor owns its state and communicates only through messages. Actors process messages one at a time, which avoids race conditions and deadlocks. In Discord's case, every server, WebSocket connection, and voice call is an actor. When a message arrives, the server fans it out to all connected sessions, and each session pushes it to the client. And this model allows Discord to scale from hundreds to hundreds of millions of users with very few changes to the underlying architecture. The fan out became a problem at scale. If 1,000 users send each one a message, you end up with 1 million notifications. And Discord improved this by splitting work across threads, using relays, offloading the fan out to separate sender processes, and using worker processes for maintenance tasks. Once the messaging layer was fast enough, the bottleneck moved to the database. Discord uses Java-based Apache Cassandra, and they migrated to ScyllaDB, a C++ rewrite of Cassandra that uses per-core sharding, has no garbage collection, and offers faster maintenance through per-row repairs instead of per-partition repairs. To reduce duplicate database queries, Discord built also a request coalescing service in Rust. When multiple users request the same message at the same time, a single database query is made and the result is shared with all subscribers. And this reduced query loads by 10 to 15 times for popular channels. Very interesting article about the architecture of Discord. The information was taken from public sources, so not from Discord itself. The last article is about statistics, about disk statistics. It's Backblaze. It's a cloud storage company and published its 2025 year-end drive statistics report. The company has been publishing hard drive failures data since 2013, making it the largest publicly available dataset on hard drive reliability. As of the end of 2025, Backblaze was monitoring over 340,000 hard drives across 30 models in its data centers. And the annual failure rate for 2025 was 1.36%, down from 1.55 in 2025. High capacity drives of 20 terabytes and above grew by nearly 8,000 units and now make up 21% of the fleet. The first 26 terabyte drives entered service. Several drive models recorded 0 failures in individual quarters, but others showed spikes. One 16 terabyte Toshiba model hit almost 17% annual failure rate, though investigation showed this was caused by temporary drive removals during upgrades, not actual mechanical failure. Our 1.36 annual failure rate means that out of every 100 drives, roughly 1 to 2 will fail per year. At Backblaze scale of over 340,000 drives, that translates to thousands of drives failures annually. And as I mentioned in my lectures, hardware will fail eventually, and this is why we need redundancy in distributed systems. Hardware will fail, and the system must be designed to handle it. So that's it from my side. See you next week.